There we go.
Yes. So
Okay, this
where
is
do we
lunar
go?
homesteading in the era of helium-3 mining. So,
Yes. Good. Thank you.
the history in the 1950s, the moon was considered to be essentially chemically similar to the Earth. By the 1970s, though, we had the Apollo samples. This found very, very little water on the moon, and so we came up with what we call the dry moon hypothesis. By the mid 1980s, there was a push to return to the moon, and the mining of volatiles, even though these were measured in parts per million, developed an interest rather than shipping material from the Earth uh, to the moon, such as water. Now, because we were starting to look at extracting volatiles in parts per million, that somebody identified that this included helium-3, which was a potential fuel for nuclear fusion. And so that led into a lot of interest about mining the moon for helium-3, and things kind of died on shifted away from the volatiles when in 1994 we discovered water at the lunar poles. There's still interest in mining helium-3 because of its value to nuclear fusion. Okay, so the seminal writings uh, define essentially the main paper that really spiked interest in the mining of helium-3 is in Space 88 conference. It was published by the American Society of Civil Engineers. It's also known as Engineering Construction Operations in Space. And this was a series of conferences every 2 years uh, on basically engineering in difficult environments such as the moon. Now, the paper, Mobile Helium-3 Mining and Extraction Systems, and basically it's work towards lunar-based self-sufficiency, uh, was by I.N. Svanatolavsk, and it was on pages 310, 321 of this Space 88 book. This paper was then popularized and expanded on in the book Return to the Moon by Harrison Schmitt. So how much helium-3 do we need? The U.S. consumes 4.254 trillion kilowatt hours in 2023. The world consumes 29.665 trillion kilowatt hours in 2023. So what we know is that through nuclear chemistry, if you take 1 kilogram of helium-3, it would produce 87.6 million kilowatt hours, assuming 50% conversion from thermal to electrical energy. So that would require for 2023 48,562 kilograms to meet all of the US 2023 needs, or roughly about 14% of the world's requirements. So if we mined 48.6 tons of helium-3 on the moon, this releases other volatiles. And the amounts of these volatiles is roughly 150,000 tons for helium-4, 24,000 tons for nitrogen, 92,000 tons for carbon monoxide, 77,000 tons of methane, 82,000 tons of carbon dioxide, and 296,000 tons of hydrogen. Also in the Space 88 conference, they had lunar agricultural requirements definition. For a 50-person base, you would need 59 tons of carbon, 122 tons of hydrogen, and 3.6 tons of nitrogen. One point I want to make on this is when they refer to the nitrogen, they're talking about nitrogen that is essentially in the plant matter. It makes up proteins. So we're not talking about the the requirement for atmospheric nitrogen that would be needed to be supplied. They did include hydrogen as what they felt was necessary for water. So the 122 tons is primarily the hydrogen in the water supply that would be needed for the agricultural system. Now, this would be a closed system. So given the amounts of volatiles that we would release during the mining of the helium-3, this would actually supply enough resources to support 100,000 new residents in space each year. Okay, as to lunar homesteading, it's my belief that space law will adopt maritime law precedents. Now, under this space and intellectual bodies in space are international territory. They are owned by everyone, and this provides legal justification for the mining of the moon. We are simply removing our share of the resources. International territory cannot be claimed. However, habitats would be viewed not as international territory, but as national territory. They would belong to the nation whose ever flag that they fly. This is similar to the way ships must be registered to a nation today. The habitats must also be registered under international law. Now, surrounding the habitat would be a buffer zone. Now, it's interpreted that this buffer zone is not a territorial claim, but the habitat would have sole control over the area within the buffer zone. Now, in international waters, an oil drilling platform has a buffer zone that extends 500 meters from the platform. So this is roughly 3/4 of a square kilometer. Now, on the moon, each square kilometer is estimated to have $330 million or be worth $330 million based on the presence of helium-3. Helium-3 is estimated to have a value of $10 million per kilogram. So we come to the issues. The simple fact is there is no commercial fusion power plant and hence no market for helium-3. Until a company actually develops a working fusion reactor, we aren't going to see interest in mining of the moon. And even once we make that decision to mine the moon, the next question is, will it be economical? The cost to put cargo on the moon is about 6 times the cost of putting it into Earth orbit. And so this raises the issue of, well, can we actually mine helium-3, produce electricity on the Earth? But would that electricity actually be more expensive than some other method of generating electricity on the Earth? Now, one thing I discovered in my research was that the method of mining on the moon in the helium-3 study used a excavator called a bucket wheel excavator. And it was estimated to weigh 18 tons. But in the solar power satellite studies, there was essentially the same excavator, and this weighed 460 tons. Now, the difference in those two masses may be something that was commented in the solar power satellite study. It seems that the bucket wheel, the cutting element of the excavator, only has a lifespan of 200 hours, which means during a normal work year, it would have to be replaced 20 times a year. And so that may be the difference between the 18 tons used in the helium-3 and the 460 tons in the solar power satellite study. The helium-3 study may not have realized that there is a lot of replacement mass that has to be added if you're going to be mining the moon. Now, this gets into another question. If the bucket wheel has to be repeatedly replaced, does it get recycled? And in that case, do we melt it down and then have it reform at some foundry, say several hundred miles from the mine on Earth? Well, could we actually have a foundry on the moon to do this recycling of the bucket wheel? And then taking that a step further, well, could we simply manufacture the bucket wheel excavator on the moon? And so that would have a dramatic impact on the cost of mining the helium-3. So if we take it to one step backwards to manufacturing the mining equipment, then that drastically affects cost. And so that leads to simply questions.
I have a question. You're finished, correct?
Yes.
Yes. So the bucket wheel excavator seems like pretty old technology. And also it's not, I mean, when the bucket wheel excavator was designed, it wasn't considered, like the lunar environment wasn't considered. Are there alternatives that people have thought about for how to do the excavation on the moon?
The only other methods of excavation that I've seen is I believe it's called a 3-drum slusher. In this case, you have a bucket, and you have it controlled by cables at 3 points, and it's just a matter of hauling this stuff over. When you say that the mining kit technology, the 3-drum bucket wheels excavators are that's the normal way that you move relatively loose material. So I don't know of any technology you're thinking of.
Well, I'm just wondering if people have considered the problem. I mean, I haven't considered it yet, so I haven't thought of other ways to do it. Well, I mean, a little bit in the research for my paper, like the snowblower idea, but yeah, but it seems like there are likely alternatives that if somebody puts a little skull sweat into it, can figure out some interesting options.
Well, this is what is done in the mining industry. So if you're suggesting that, well, we need to rethink the mining industry, and then you have to come up with a reason why this is more appropriate on the moon than it is here on Earth. If you, in effect, if you're saying, well, maybe we should find a way to mine material more effectively here on Earth, that's a nice idea. And if you have any ideas, any possible solution to that, I'm sure people will be interested.
Yeah. So I have one more question, which is, I didn't understand how does the extraction of the helium-3 happen? So you're extracting the helium-3 on the lunar surface and then shipping back helium-3, correct? You're not just shipping back tons of material. So
that's right.
How does that extraction process work?
It's think of an hourglass. So the excavator would dig up the regolith, put it on a conveyor belt. The conveyor belt would then run it to the top of a bin, drop it into the bin, and this is in vacuum. Then at the bottom of the bin would be a neck, as it were, like an hourglass, and the regolith would then sift through that neck dropping into a second chamber. Now, the second chamber has a very slight atmospheric pressure, and so you're now heating the regolith to about 700 degrees, I think it's 700 degrees Celsius, within this atmosphere, and the atmosphere is being circulated to remove the volatiles. And then the second chamber basically is like the first chamber, that's like an hourglass. The regolith is dropping through again to a third chamber beneath it, where a conveyor belt takes it away, and then it gets distributed back onto the lunar surface. So by the third chamber, the volatiles have all been removed. Now the idea here is that the two necks, you have material sitting on in the first bin on top that blocks the atmosphere from going up, and then the material on the bottom blocks the atmosphere from going down.
Yeah, and then after you have the mixture of volatiles, then you separate out the helium-3 by cooling it or something, like fractional distillation, basically.
Yes.
Yeah. Okay. Thank you.
Ben? No, you're mute.
Yep. Anyway, I just want to say, Stuart, one of the big problems with designing mining equipment on the moon is 1/6 gravity, right? So most of our mining equipment uses its mass in relationship to our gravity to kind of hold it in place while it moves the Earth. If you try to use a lot of traditional mining methods, it just ends up pushing the machine around more than it does moving regolith. So we have to be kind of clever in how we remove the material without actually moving the mining equipment as well, unless you wanted to add like a significant amount of mass to the mining equipment to kind of lock it in place.
Yeah, or you could use like a drag line, right? You could.
Yeah, but you know, again, that adds complexity and cost and everything else. It's just, you just can't use traditional mining techniques without significant modifications on the moon. So that's one of the reasons why the bucket is used, because it doesn't necessarily, when you're using it, it doesn't necessarily push the equipment around.
Mm.
Okay, Frank?
Yeah,
Yes,
there's one thing too with mining on the moon that I haven't really heard too much about, but it came up. Apparently, the Earth's atmosphere acts as a lubricant with material. So it is actually much, much more difficult to dig material in vacuum.
Yeah, I was going to ask, given that dust behaves differently in a vacuum, that the grain geometry is incredibly sharp, and that we have a huge amount of volume to process, do you foresee any like major like wear over the equipment, and how we could possibly like mitigate it for lunar applications?
Well, the numbers that were given of 200 hours for the cutting element, I'm presuming is actually Earth-based. And so that in itself, it shows a significant amount of wear. Key issues would be probably a constant replacement. And I would wonder if we were going to construct this mining machine on the moon, what key elements might have to be imported from the Earth, such as ball bearings.
There's another aspect used for mining on Earth, is that sometimes they have to reload the bins of the excavators with welding rods.
From what I understand, the bucket wheel is worn down as it circulates, and I think in part they can encounter boulders, they can encounter rocks that causes issues, that breakage. So periodically it has to be replaced, and the number they were giving was 200 hours.
That's not a
And
lot.
the work period was 4,000. The work year was 4,000 hours.
Yeah.
So we really have to understand the mining operations here on the Earth, see what we can do about sending it, transferring that knowledge to the moon. And then once we get on the moon, we still have to work out, quite possibly coming up with solutions to deal with the vacuum and with the material itself.
Good. Ulf?
What about the economic value of the other volatiles other than helium-3? I mean, not just for possible export to Earth, but also for substituting imports to the moon from Earth.
Okay, I'm not sure I understand the question. One of the concerns I have is right now we're going with the trend of wind, solar, storage, and grid. And so helium-3 fusion has to be competitive with that system. And
Right.
solar power is hitting now about 6 cents per kilowatt hour, while the helium-3 was estimated at having a cost of basically as fuel 12 cents per kilowatt hour. So it would have to readjust in that regards. But then the long pole in the renewable energy sources is storage, which can add like another 10 cents per kilowatt hour. So it would be 6 cents plus 10 cents to 16 cents per kilowatt hour. Now, as a California resident, I pay 30 cents per kilowatt hour. But half of our utility bills are very elaborate, and so they show that about half of that cost is in the grid. So at the power source, it's about 15 cents per kilowatt hour.
Right. What I meant was that when you extract helium-3 on the moon, you get lots of other volatiles. Also, do they have some economic value?
Realistic for Earth, no, but for the moon itself, it simplifies the cost of building on the moon. A key thing is nitrogen. It was in the O'Neill type space settlements. The atmosphere was considered to be one of the major cost elements of O'Neill settlements, because it was assumed that there was no nitrogen on the moon, and that all nitrogen was being brought up from the Earth at $100 a pound.
Right.
So that would be a potential export from the moon to an O'Neill settlement.
Yeah, right.
So the existence of the volatiles there would mean that the mining town will be cheaper to establish, I guess.
Ultimately, I think the first area that's going to be mined, though, is the poles for water ice. As I said, the cost from going from the Earth to the moon is about 6 times the cost of going to low Earth orbit. It's one of the early concepts for the moon was to act as a propellant depot to generate propellant. And because we could carry the propellant, it's cheaper to carry the propellant from the moon to low Earth orbit that is to launch the propellant from the Earth to low Earth orbit. So that we could reduce the cost of getting material to the moon if we had a dedicated lunar shuttle using lunar propellant and carrying cargo from low Earth orbit back to the moon, and then bringing propellant back to low Earth orbit. And so instead of 6 times the cost of getting cargo from the Earth, the cost would probably drop to, say, twice the cost of getting into low Earth orbit.
Thank you. Stuart?
Yeah, I was just going to mention that, yeah, the economic value is to get it to low Earth orbit. It's not just to get it to Earth. It's like you can shift, like shipping stuff to low Earth orbit from the moon. Apologize for the cars. There should be a big economic value for anything you can ship to low Earth orbit that they need. And also, I mean, when we're colonizing the moon, there's likely to be more and more stuff, more and more people living in low Earth orbit as well. So there's a bigger market.
Yeah, well, the question of manufacturing, the NASA focused on low mass, high value items, and the two areas they found of interest was pharmaceuticals and electronics. But the amount of mass needed there wasn't so large that it really involved shipping raw materials from the moon. Taking it to the step of creating the space stations and basically space factories that would produce the pharmaceuticals, electronics, that's something that makes some sense to send from the moon. But there is the key issue is having some sort of economics, some sort of value on the moon that we could ship back to Earth. And that's difficult because if the cost is $100 a pound to get to Earth orbit, and then we assume that really that is also included in the cost of returning, so we might send up an empty shuttlecraft to low Earth orbit to bring back some material that is manufactured on the moon. Well, then that material has to be more valuable than $100 per pound.
Well, no, I was thinking about just like shipping oxygen to the space station or any low Earth orbit habitats, because then the oxygen doesn't have to be brought up from the Earth. It can just be shipped from the moon.
Yeah,
So
and the big value was always seen as the propellant needed to reach Mars. Because I think the typical chemical Mars rocket was about 2 million pounds.
Quick comment, Ben.
Yeah, I was just wondering, James, if in your research, did you see any numbers for how much regolith would have to be moved and processed
Oh yeah,
per ton
it's huge, but the mining machine was essentially scaled down from a commercial miner, and again scaled down, and it was to process 4 million tons
per year?
per year, and that produced only 33 kilograms of helium-3.
Right. Okay.
But that's $330 million.
That's a very good point to stop there, because it's time for the next